All right, let's start talking about when things translate and roll at the same time. Okay, so we've looked at translational motion. And by that we mean literally no rotation occurred. So let's call this some point A and maybe this some point B. And this could take some path like this. And as long as those lines, so this is going to be hard, stay parallel. Oh, try that again. As long as they stay parallel. So we'll make it a little bit easier. Give it a path like this. Then A prime is in the same place with respect to B, or B is in the same place with respect to A. So if we made a vector from one to the other, we'd see that the angle doesn't change, the magnitude doesn't change, nothing. That's what we call purely a translation. A rotation is when we take something and give it an axis to rotate about. So we could rotate this about this axis, or it's a little bit easier, right? If this had some even mass distribution, it's a little easier to rotate if we rotate it about the center. But most things tend to do both. And then we're going to start off talking about a rolling wheel. We're going to talk about rolling first. So rolling, first of all, is when we combine translation plus rotation. Or to describe it, we're going to have to include the translation and the rotation. Something that has both translation and rotation we'll call general plane motion. So you might see that in the future. Just referred to it in that manner. But here we're going to consider an object that rolls smoothly. And by that, it means that it's not bouncing. It's not coming off the surface. Let's go ahead and get a circle drawn up. If we look at an object rolling on a surface, we can say the center of mass moves off at some velocity or some acceleration, right? And goes through some displacement. But some point up on the edge of the circle or the disk or whatever it happens to be, or anywhere on the inside, right? Put it over here. If I wanted to describe this point, let's call this point P and this point Q. I could draw a vector from R to Q and a vector from R describing, we call this the center of mass. We can say P with respect to the center of mass. We're going to look at this point right here and figure out how to discuss its motion, because whereas the center of mass right here, we can literally ignore the rotation motion as it moves to some new location over here. The center of mass just moved like a solid mass. You can just think it didn't have any rotation at all, basically. It's in some new location, COM prime. But this point P had to have moved and rolled over. And basically, we can't describe what happens at this point P to get it down here to P prime as just rotation. We can't describe it with just translation. We have to describe it with both. And so that's what we're going to do. Let me draw this set again real quick. Okay, here's our wheel at one position. And some later point in time. If we say that the velocity of the center of mass would Well, okay, how should I say this? We should describe the velocity of the whole thing translating by looking at the center of mass. And so that is going to remain the same. If it moves off with some constant velocity, the velocity would unchanged. If it accelerated with some acceleration or some alpha, then that velocity would increase, but it would just increase from the center of mass, right? So that's one way to describe the translational aspect of it. But if this thing's moving like this to get from point 1 to point 2, um, we should note that if it travels some angle theta, so if let's say there's some point P right here touching the ground, point P. If this point moves up to over here, P prime, that means that it went through some angular displacement, right? There's some theta here. To rotate and roll into position 2, it had to go through some angular displacement. And we'll call this angular displacement, this thing right here, this arc length, or we'll call this arc length S, and we can describe that using the angular displacement. S is equal to the radius times theta. So that's one relationship we'll need. And then we can also take a time derivative. Bet you didn't expect that. Just kidding. To get that the velocity is equal to r omega. Okay, let me draw. So both of these are good equations we're going to have to use. This describes a point on the edge when we have a rotation, but when we have something rolling, we can look at it like this. We can say there's a pure rotation going on plus a pure translation, and that's going to equal what the book is going to call a rolling motion. More specifically, or more generally, a general plane motion. All right, what does that look like? Let's draw some pictures. Let me get 3 circles going. Make sure they're circles. All right, so we're going to look at the pure rotation on the first circle. The second circle is going to represent our translation, and then all 3 put together is going to represent our rolling motion. So if we look at a pure rotation, it's rotating about the center, and we can look at it in a different way in a moment, and we're about to. But for now, let's just say, okay, it's just rotating about this point O with some angular velocity omega. If we look at some point up at the top, it's going to have some tangential velocity. And whatever this velocity is going to be equal to the velocity of, equal but opposite to this velocity right here. Right? Just like we would have a tangential velocity here, we'd have a tangential velocity here. So this is, we'll call this P. V at P is equal to the opposite of this V up here. And your book calls it T, I'll call it a T. If we add the translational aspect, we'd still look at the center of mass, and we'd see that the center of mass is going to translate with some velocity like this. Now, every point on this is going to move with that same velocity. I'm drawing these 2 points first. It's the 2 points we're interested in, but right, everything moves with this same velocity. That's the definition of translation. And when we put them together, we get that the center of mass moves with some velocity. Equal, same thing right there. We see point P would be on the ground, and if we look at it at this instant, so at the instant considered right here, it is basically a fixed point, kind of. We're still rotating about here. We're going to use the trick that this can be looked as a fixed point in just a moment. It'll give us another way to view this. But this point down here, point P, the velocity is 0 at that instant. What we get is actually a velocity at t that is twice as long as this velocity right here. So we say the velocity at t is equal to 2 times the velocity of the center of mass. And I think the next drawing will help make sense of that, but just think about it. If we had something sitting like a ruler and it was falling on the ground and it teeters over this way. As it teeters over, the velocity of the tip is going to be moving faster than any other point, right? It'll actually be moving twice as fast. So if I call the center of mass V, the tip at, if it was equally spaced, would be 2V. And then down here, V is equal to 0. There's just a rotation. So that should help. Yeah, here we go. We have a pure rotation plus the translation gives us the whole picture, general plane motion. All right, there's another way to look at this though. We can say, what if we look at rolling as just a pure rotation? We're going to consider that by looking at just the point at which it's making contact with the ground. Yeah. So there's our ground. Here's our center of mass. And if we're going to rotate about this point P on the ground, let's take a look. I'm going to draw some lines. We'll do a little geometrical interpretation. But what we get would be that the velocity of the center of mass would be like this. The velocity of the top would be 2 times that. Call that point T. And what if we look at some other points like this, 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 or this? Well, the velocity is always perpendicular to the what we can call the position vector to that point. So if I draw straight lines to them, so this is perpendicular, right? This is perpendicular. Well, guess what? The other ones are going to be also. Then what I get is a velocity vector at this point, perpendicular to that line. A velocity vector at that point. It's a little bit longer, perpendicular to that line. A velocity vector almost, but not as long as this one, perpendicular here. And then similarly on the other side. A little long. And this would be just a little guy right there. So what this gives us is the fact that this right here is half of this. So we can say the velocity at the top is going to be equal to r omega, right? But r in this case, we have two of them. So put a 2r here, and we get the velocity of the top is equal to 2r omega. What does that tell us? Well, this is the definition of velocity, right? The tangential velocity. And it tells us that the velocity of the top is going to be equal to 2 times the velocity of the center of mass. And what's interesting is it doesn't matter where you measure it from, omega is going to be the same. Omega is not a value that changes. If we measured omega about here for the same object and then measured omega from right here, it's going to be the same. So that's why we can use this omega right here for either situation. Why would we use this? What if they gave us a vehicle is moving along and let's say the speed is equal to 20 meters per second. Well, we can go ahead and attach that right here and say that the center of mass is moving with a speed of 20 meters per second. We could figure out how fast that top of the point is because it's going twice as fast as the center of mass. This is making contact with the ground, so at the instant the velocity is actually 0. And if you had that speed and this radius right here, you can find omega. And then use that omega to solve some more of your problems or do kinematic equations, right? So this could be a starting point for some of your problems. What you'll find out is that if you did r omega, or you looked at the velocity of in this manner, or in this manner, that you get the same omega. Same omega, same omega. So here's our omega right there. All right, y'all.